And hello and welcome to the May edition of Comet Watch. Unfortunately, Neil Norman can't be with us this month because his son's not feeling very well, so we wish his son a speedy get well soon, and that Neil gets back with us fairly quickly. So, I guess we're going to get kicked off with the usual gubbins, as they say, and myself and how bad-mannered. I forgot to introduce my co-host. I apologise.
Hello, it's Mary McIntyre.
Okay, so yes, we have a special guest with us. We're hoping to have two, but we'll see what happens. And he's an old friend of Comet Watch, so I'm sure you'll be glad to hear him back, because I'm always glad to have him on the show. Now, latest discoveries as of the visual observations page from the BAA. April 9th, Warchart Boomplod reports a Kreutz comet in real-time C3 images.
April the 15th, Warchart Boomplod reports a Kreutz comet in real-time C3 images.
April the 17th, 2018 F4 redesignated as a comet. Yay!
April the 18th, recovery of 2011 CR42 periodic Catalina as 2018 H1 reported.
April 18th, Warchart Boomplod reports a Kreutz comet in real-time C2 images.
April the 20th, 2018 EF9 is found to show cometary features.
April the 21st, Warchart Boomplod reports a Kreutz comet in real-time C2 images.
April the 22nd, Warchart Boomplod reports a Kreutz comet in real-time C3 images.
April 23rd, Warchart Boomplod reports a Kreutz comet in real-time C2 images.
There was another April the 22nd, Warchart Boomplod reports a Kreutz comet in real-time C2 images.
Okay, and there's another April 23rd, Warchart Boomplod reports a Kreutz comet in real-time C3 images.
April the 26th, discovery of 2018 H2 periodic pan-stars reported.
April 27th, Warchart Boomplod reports a Kreutz comet in real-time C2 images.
And April the 30th, Warchart Boomplod reports another Kreutz comet in real-time C2 images.
May the 3rd, Rainier Cratchit reports a Marsden Group comet in real-time C2 images.
And May the 4th, Warchart Boomplod again reports a Kreutz comet in real-time C2 images.
May the 6th, Warchart Boomplod reports a Kreutz comet in real-time C3 images.
And the 7th of May, the site was updated.
Now, if there's no recent updates, you can always try on the German Comet Group or Yasushi Yoshida's page for information, or the Liga Iberoamericana de Astronomía for observations. So we're going to switch and start doing the current comet magnitudes. Now, I swear I have not. All I've had today is tea and coffee. Current comet magnitudes May 2nd, an observable region May 2nd. We'll kick off with a comet I actually imaged last week. Pan-STARRS 2016 M1. Magnitude 10, bright, 55 degrees north to 80 degrees south. It's a when visible morning. Last visual observation was April 2018.
Pan-STARRS 2016 N6, that's currently magnitude 12 and steady, observable 60 degrees north to 0 degrees north. That's best viewed in the evening, and the last reported observation visually for that was May 2018.
Pan-STARRS 2016 R2, magnitude 12, fade, 55 degrees north to 15 degrees north, early evening, last observed May 2018.
Then we have 48P Johnson, magnitude 13 question mark. That's trending towards brightening, observable 35 degrees north to 75 degrees south. That's best viewed in the morning, and that's not yet been observed visually.
And 240P neat, 13th magnitude question mark, steady, poor elongation, not yet observed.
Then we have 29P Schwarzman-Wachmann, currently 13 question mark. That of course varies. Observable 25 degrees north to 60 degrees north, visible in the morning, and the last visual observation was in October 2017.
Okay, Pan-STARRS 2015-01, 13th magnitude, fading 60 degrees north to 0 degrees south. It's an all-night object, and it was last visually observed in May 2018.
Then we have Atlas 2017 T3, magnitude 14, question mark. That's brightening, currently in conjunction, so not yet observed.
Okay, 66p Detroit, 14th magnitude steady, 5 degrees north to 90 degrees south. It's a morning object, the last visually observed April 2018.
Then we have 185p Petru, that's magnitude 14 and fading, observable 15 degrees north to 20 degrees south. That's visible in the early evening, and the last visual observation was March 2018.
Then we have Johnson 2015 V2, 14th magnitude, fading, 40 degrees south to 90 degrees south. It's an early morning object, and last visually observed September 2017.
And then we have 364p Pan-STARRS, magnitude 15, question mark. That's brightening, observable 55 degrees north to 10 degrees south. That's observed in the early evening, but no visual observations yet reported.
And finally, but not least, 21p Jacobini Zinner. I think that's about right. 15th magnitude, question mark, bright, 50 degrees north to 15 degrees south. Early morning, not yet observed. Now, obviously, the observable region is an approximate indication of the latitude at which the comet may be seen. Under good conditions, comets may be visible outside of this range. The period when visible is for the UK, and if the comet is visible from the UK, otherwise for 40 degrees south, or the equator as appropriate. The last visual observation is as received by the BAA comet sections. So do look at some of the other places, like the German group, your CG Yoshida's page, particularly Yoshida-san's page, because he does have a lot of up-to-date information there, so he may have stuff we've missed or may not know about yet. So now we get to the fun bit. Would our returning friend care to introduce himself or reintroduce himself?
Well, this is Jim Scotty from the University of Arizona in Tucson, comet hunter, comet observer, always having fun talking to you guys.
Now, I know that we've always been wanting to do a certain subject, and that was since March we've been hearing about Schultz's star, which, let me pull up the page because I want to make sure I hate getting my information wrong. Okay, where are we? Now, they said that this star actually passed. It was a near miss with our solar system about 70,000 years ago, and that it was thought to have actually gone through the Oort cloud. Jim, could you just give us a little bit of sketch on the Oort cloud, if possible?
Well, the Oort cloud is a region of space where comets were ejected to in the early solar system by mostly Uranus and Neptune, I believe. And it's really defined by how close stars come to the sun. Anytime a star passes through the Oort cloud, it's going to disrupt the orbits of a lot of the comets that comes near. Plus, it tweaks the motion of the sun and the other planets a little bit too. So all the orbits of the Oort cloud comets get shifted around a little bit because of a close star pass. So over the 4.5 billion years the solar system has been here, I'm sure there's been a lot of much closer approaches than this object that probably disrupted the Oort cloud a little bit. But the Oort cloud is where a lot of the long period comets come from. Jan Oort figured out or noticed that the best orbits for the long period comets all appeared to be very nearly parabolic, but a lot of them were elliptical with an aphelion that was way out around 100,000 AU or more, and others were on parabolic orbits. So he deduced that there was a cloud of comets out there that the pass of nearby stars, or maybe the galactic plane or something like that, would tweak the orbits of some of those comets and make them fall in essentially all the way to the sun. so that we could see them from time to time.
Now, the figures that I'm seeing for the Oort cloud is ranging from about 50,000 to 200,000. So that is pretty much, well, the closest star to us would be Proxima Centauri. So the cloud itself reaches out as a halo. You need pretty much 3/4, maybe half the way to Proxima or out even Alpha Centauri. So that is quite a volume of space really that's occupied.
And of course, Alpha Centauri and its little cohorts there are just the closest at the moment, and the next closest is a little bit further away. But space is fairly big there, and there aren't many stars there, luckily, to disrupt the Oort cloud that we see.
Now, I know that this particular candidate has actually been has been tracked back through time, and so that we actually know where this one is. So, because what they were saying was, although it went past us about 70,000 years ago, it's one of the ones we can actually still track, and it's only about 20. The pair is actually 2 stars. It has a red dwarf companion. A brown dwarf companion. Oh man, I've got Lester on the brain tonight. I should not watch Red Dwarf before I do shows. But this is an unusual star in many respects because of the brown dwarf companion as well. So when it's actually gone past or even gone through a part of the Oort cloud, it would have probably given quite a lot of stuff a substantial kick.
Yeah. Also, it pulls on the sun as well a little bit, and shifts the orbit of the comets, of all the comets, a little bit by shifting the motion of the sun just slightly. Interesting side effect there.
Yeah. As I say, I suppose a lot of people have got used to the idea that of just huge distances and just molecules of gas being predominantly out there. No one's really thought about anything could actually sail past the solar system and actually affect us. I think mainly because of the sheer amount of time involved. 70,000 years ago, probably very simple life on the Earth, I would have thought. Certainly nothing there to actually watch. I suppose it would have probably been visible.
Yeah,
I've seen a nice graphic of it, but I don't know how realistic the graphic is.
Yeah. I'm looking.
Early humans and some of our relatives were certainly walking around. I'm not sure how bright this star would have gotten, actually. So.
Well, I know that on one of I think it may have been the Earth Sky Post. They reckoned it would have been fairly prominent as a bright star in the sky. But as I say, the main star was certainly spotting brown dwarfs. We only know about those from anything they actually perturb at any particular time. So having a companion star with a brown dwarf probably would it cause the main star to blink, I wonder?
It might if you're in the plane of the brown dwarf's orbit. That's how most of the exoplanets have been discovered over the recent years, by watching the star dim slightly as the planet passes in front of it, which is fairly difficult in the old days from the surface of Earth, but from space it's a lot easier to do.
Oh yeah. Gaia has certainly brought home a heck of the satellites we have, including Gaia, are certainly bringing back stuff that we never even dreamt of, and they're resolving distances even better for us. But it's certainly an interesting thought to think that perhaps the comets we're seeing today, and even some of the ones that get captured by Jupiter as short period comets, probably owe that to this star and its brown dwarf companion ploughing through the Oort cloud.
Yeah, that's certainly something to think about that we hadn't really thought about before, because it does take something like 500,000 years for a Oort cloud comet to orbit the sun.
Even if it's because most of the ones that we do get tend to either, if we're really lucky, they're on a parabolic, and it's an orbit we can track. And unlike some of the really nice ones, we may never see again because they're just heading out of the solar system full stop. They're on a hyperbolic. Certainly, makes you wish you had a time machine, I suppose. Go back and see these. Maybe you'd be in space itself, and that way you can alter the plane of reference and look for these things.
I mean, do we know how densely packed the Oort cloud is? Because I know I hadn't actually realised until reading up on this subject how far out it actually reaches. But I was always curious about how dense it is. Do we know that yet, or?
Well, based on the rate that we see long period comets coming in, we have at least some idea of how many comets there must be out there. I don't remember that number off the top of my head, though.
So the theory is that it's a spherical cloud that surrounds the sun. So you still have to be reasonably dense, I think, given the number of comets.
Well, compared to what we would call dense, it's actually fairly sparse.
Yeah.
The number of comets per square astronomical unit is probably not a very big number, really.
Yeah. That's a good point.
Cubic astronomical unit. Cause
just the distances covered are so vast, it means there's a lot out there.
Well,
yeah, that certainly is.
I pulled up one of the NASA sites for about the Oort cloud, and it looks like we're talking about 1,000 AU to 100,000 AU thickness. So that's just well. Let me see if I can get that graphic saved. Image address. Here we go.
That's 10 to the 15th cubic AU, roughly, plus or minus a little bit. So, if there's one comet per cubic AU, that's 10 to the 15th comets. I don't remember how many there are, but it is fairly low density by that standard.
Well, yeah, because they reckon WISE. So there's 7 times more long period comets measuring at least 0.6 miles, 1 kilometer across than previously predicted. And the long period comets tend to be up to twice as large as Jupiter family ones. So
yeah, you have more opportunities to discover the Jupiter family comets, where you only have one chance to find the long period comets. Also, the long period comets probably haven't been close to the sun ever before, or at least recently. So they're more likely to have volatiles near the surface that haven't been baked out of them. So
that is one of the nice things, I suppose, about having the Oort cloud. That there is the opportunity to have a fresh comet that hasn't really picked up any dust from the inner solar system, or as much dust as periodics, short period comets do.
Well, it's actually a little funny here, because when you look at the formation of the solar system, the Oort cloud comets probably formed inside of the orbit of Uranus, whereas the short period comets were formed out beyond the orbit of Neptune. So the comets that we see coming in from the farthest today probably formed closer than the comets that we see closer today.
Well, really, that's interesting.
Well, yeah, it sounds quite logical. Oh my god, I'm doing Spock now.
It's really weird to think about it. The first time I realized that, I was like, wait a minute, oh, that's pretty cool. So, the comets in the out beyond Neptune, the trans-Neptunian objects that we still see a lot of today, orbiting stably out there, that feed the Jupiter family, they have been out there colder, farther away from the sun for a long time, and these long period comets were ejected out there sort of into the deep freeze, where presumably they've been relatively well preserved for the age of the solar system.
Now, according to one of the NASA sites, they estimate more than 1 trillion icy bodies for the Oort cloud. That's interesting.
That seems like a small number.
Yeah,
for the distances that we're talking about, for just the density in terms of how far out it extends, that's not as many as I thought there'd be.
well, yeah, it does seem to be kind of on the low side, really, considering this is actually something that encloses the solar system in a bubble, so to speak.
Yeah.
Yeah, very large bubble.
Well,
Yeah, considering that it's on the order of 15 trillion, 10 to the 15th, which is 1,000 trillion, right?
mm-hmm.
That's how many cubic light astronomical units there are out there in the Oort cloud, roughly. So that's very few comets per cubic AU out there.
Theoretically, they reckon if Voyager 1 travels at 1 million miles a day, it would take the spacecraft about 300 years to reach the inner layer of the Oort cloud, and 30,000 years to get to the far side.
Crikey.
That's interesting thought, that. I think we really do need warp drive or a decent impulse drive. Well, I think one of the things that would be really, really nice is if we could actually, although New Horizons, as I recollect, is actually not going out that far for missions, because the objects it's looking at is relatively close in to the edge of the solar system. It's one of the trans-Neptunian objects, I believe, that they've picked.
Right, it can't last all that long, and I don't know how far out they can really even communicate with it, but it has a limited lifetime in there, and it's going to have to be. I mean, the next object it's coming up on here pretty soon is only less than 40 astronomical units away from the sun. So
yeah, so it's not even going to get as far as the Oort cloud, which is a shame, really.
Well, it's studying the trans-Neptunian objects like Pluto and this new object I forget the designation of.
It's going to be an interesting. I'm really looking forward to seeing some of the images that is going to come from that particular mission, because a lot of people always thought it was a lot of the comets were just trans-Neptunian objects, and I think it was Jan Oort that really took it to the next stage back in the 50s, about about this halo around the solar system being the reservoir of comets.
Yeah, he was the first to recognize that when he took a look at the well-determined orbits of long-period comets, and as I mentioned earlier, discovered that about half of them were on elliptical orbits that would, they were a very long period. The other half were on hyperbolic orbits, but they were all very close to an eccentricity of 1, which is parabolic or very, very long elliptical. And from that, he was able to estimate roughly how far out the Oort cloud, what became the Oort cloud, actually was. Somewhere on the order of 100,000 astronomical units.
Yeah, but it was interesting to see that his theory. Oh yeah, I know it's still considered a theory, but we're pretty much accepting the fact that the Oort cloud is what it is as predicted. It will be confirmed as predicted.
Yeah, the details I'm sure will be interesting to discover once we can explore it more thoroughly. But we already have, I think, a pretty good idea of that there is a cloud of objects out there supplying what we see as the long period comets, and it's roughly uniformly distributed. I imagine there's some asymmetries due to comet or star passages like this one we were just talking about. And others that would probably warp the distribution just a little bit for a while before it, gets back to its sort of steady state mode over the years.
Is it too far away to have any orbital resonances with any of the bigger planets?
But I don't think it'd be sort of like expecting Mercury to be affecting the orbit of Neptune that much.
Okay.
Even more extreme than that, really. I think mostly it would be external phenomena like the plane of the galaxy or the passage of nearby stars. or if you had a solar companion, like there might still be. We haven't completely ruled out that there might not be another planet or object that was on the order of, say, the size of the outer planet Saturn or Jupiter, or maybe even I think we've probably eliminated brown dwarfs from being in orbit around our sun, but there still could be a good-sized planet out there that could be pushing and pulling on things a little bit.
I have to admit, given the occultation enthusiasts that we have in astronomy, if there was a brown dwarf, I think it would have been discovered, and certainly something would have. So a more powerful telescope or a space telescope would have been detailed to look at it, because it was certainly it would cause an occultation of another star to announce its presence, I would have thought, if it's in the right plane.
Maybe, but also we've searched for brown dwarfs orbiting our own star with the infrared space observatories that we've had, like WISE most recently and ISO before that. So they have been hunting for those objects in case they were out there to be found. I'm not sure what their lower limit on a size for detection would be, but I think they've ruled out a traditional sort of brown dwarf sized object, but not necessarily a Neptune sized object or Saturn sized object or something like that.
Well, I know, slightly straying, they think there is another planet out there, and they think it's a large gas giant, and they're saying it has to be very far out in the solar system to have avoided discovery. Now, the mathematics say that it's out there, and it's really a case of getting the observational data, I suspect, just to prove it. It's going to be awfully dim.
Well, it's based on having seen some scattered disk objects. Scattered disk objects are objects that are out beyond the trans-Neptunian region that's sort of 40, 50, 60 AU from the sun, that they might be more elliptical orbiting objects that get out to maybe a few hundred AU and might come in close enough to interact a little bit with Neptune. But the sample of objects that they had found were unusual. It was statistically unlikely that if you found 6 objects, they'd all be in those kinds of orbits. So they inferred that there was a planet that was putting them into that sort of common orbit that they were seeing, orbit plane they were seeing. So I'm not 100% convinced yet about this, because I think there's other possible explanations that might still exist. For example, observational bias. If they're surveying in a particular area of the sky, you might preferentially find those kinds of objects, and I'm not sure that they've completely ruled that out. Maybe they have, or it's really hard to say for sure.
Wasn't there a theory that it could also be lots of small objects having the same overall gravitational effect as one big one? I'm sure I remember reading that at the time that story came out.
It's harder to imagine how that would work, but I don't know. You can do a lot of arm waving still, I think, and possibly come up with an explanation. My arms are moving all over the place here.
And of course, the other thing is the outer planets. They affect the comets. They can change courses, which is something we're well used to with Jupiter anyway. The Jupiter effect. Let's give it a nice handy name, the Jupiter effect. Let's have a comet come in, Jupiter either captures it and it becomes a periodic, or Jupiter nudges it in such a way that it goes into perhaps a long orbit and maybe even leaves the solar system. So it can be benign, or it can be a little devil sometimes.
Yeah. Well, when I first got into comets, they were trying to explain how the Jupiter family of short period comets got to be there, and the source at that time would have been the Oort cloud. How do you get the Oort cloud comets to become Jupiter family comets. And the trouble was that the Oort cloud comets, one thing that distinguished them is that they come from all directions in the sky, a uniform distribution roughly. So they can come from, the North Pole just as often as they come from, somewhere near the ecliptic, for example. Whereas all of the Jupiter family short period comets were in low inclination orbits. And the only way you could get that was by somehow very biasedly selecting some of those Oort cloud comets to go into those low inclination orbits. Otherwise, we should have Jupiter family comets that are orbiting backwards, like the Oort cloud comets do. So that was a big puzzle, and there were a lot of papers by guys doing their best to try to figure out how you could do that, and they couldn't come up with an answer. It was more than a factor of 10 off from what we were actually seeing. So this is where the Kuiper belt, which actually I think should be named after a guy named Julio Fernandez, should be the Fernandez belt, because in the early 1980s he suggested, by analyzing the orbits of short period comets, that there must be a reservoir that's a low inclination reservoir, and why not be out just beyond Neptune? And it was more recently that we've started finding them. And so you get these objects that orbit just outside of Neptune that are slowly pushed and pulled by the outer planets a little bit, and eventually they interact strongly with Neptune. They get too close to Neptune, and Neptune can pull them in and make them Neptune crossing rather than Neptune approaching, and possibly even Uranus crossing, and eventually they turn into what we call nowadays the centaurs. I really got interested in this shortly after we discovered Pholus, which was the second centaur ever discovered. And then not long after that, I found the third centaur, and we really got interested in studying the motion of centaur asteroids, which are asteroids that orbit around in the outer solar system. There really isn't a 100% solid definition, but I draw the line at approaching Jupiter. So any asteroid that doesn't quite approach Jupiter close enough for it to take over its motion would be considered a centaur, as long as it crosses the other outer planets. So these things can wander around for millions of years until they go through resonances. They get pushed and pulled around a little bit, and a small fraction of them get pushed down into Jupiter, where Jupiter takes over and they become Jupiter family short period comets. So it's sort of a long story there.
Yeah.
With lots of, there's no kind of hard and fast definition for them then. Explains why I couldn't find a proper answer when I was doing my astronomy GCSE.
Yeah.
Having said that, I'm sure most of us are glad that we have the Jupiter family of comets, because they tend to be our most, reasonably reliable visitors. Sometimes
they keep coming back.
Yeah. And just 1 second, just getting a message. We may be having somebody join us in a couple of seconds, so I'm just going to place us on pause for just 1 second, okay?
Okay.
Okay, sorry about the short break there. We were just seeing if Rich Krawski was going to be able to join us. Unfortunately, he can't, but never mind. There'll be another time. Okay, where were we? The Oort cloud, Jupiter family comets,
centaurs,
yep.
Trans-Neptunians. In a respect, I suppose we're lucky that we have this rich reservoir out there. It makes you wonder: do other solar systems have it? Now, thinking about the fact that our Oort cloud goes pretty much halfway to the Centauri system, could we be sharing it with the Alpha Centauri system?
I don't think so in that sense, because the Oort cloud comets are loosely bound to our sun. And the relative velocity of stars with respect to neighboring stars that are nearby is much higher than the orbital velocity of the comets. So they might tweak the orbits of some of the Oort cloud comets a little bit, maybe enough to be recognizable. But I don't think they'll steal them, for example. And there's no way you can really share them between two stars. I mean, there might be. It's sort of like looking at a simulation of two galaxies running into each other. You can see the gravitational distortion of the disk of all the stars and gas and dust around both of those galaxies as the gravity of the other galaxies interact with all that debris. So you're going to have that kind of thing going on with the Oort cloud, where the orbits of all the objects in the Oort cloud are going to be, tweaked by a little bit from all the neighboring stars, especially the big ones.
But not as big as by something.
But not stolen.
Yeah.
Yeah, and not knocked out of orbit very often.
Yeah.
Some of them will be, of course, because we see in the Oort cloud something like half of the long period comets that are coming straight in from the Oort cloud are on slightly hyperbolic orbits, so they are leaving our solar system. But the other half have been moved into slightly smaller orbits that will have them come back in a reasonable amount of time. So some of these comets become the shorter period, long period comets, like Halley's Comet is.
Yes, that famous one. Yes, and of course it's not going to be back until at least 2061 at the earliest.
Yeah, I'll only be like 101, so I'm expecting to see it again.
I should be slightly younger than that, but yeah, I touch wood. I'd like to see it again. It wasn't the most brilliant apparition in the 80s, but of course, if you were very careful and you knew where to look with a decent instrument, you did have a chance. And of course, we had the space probes, the Vega probes, Giotto, amongst others that went there. I can't remember what the Japanese probes were. I know the Vegas were Russian, I believe.
Yeah, there were 3 spacecraft, the European and our American one, and one Russian one, I think, that made close approaches to Halley's Comet on the way by. I made sure to make sure that my daughter actually saw Halley's Comet. She was less than 2 at the time of its closest approach, and I put her eyeball up to the eyepiece of my telescope. And whether or not she remembers that comet in particular it doesn't really matter to me anyway, but when she sees it come back, she can safely say that, yes, I saw Comet Halley 76 years ago.
Because I never saw it. I was out there every night. I used to get up in the morning and study teletext Halley watch page, and I was the only person I knew that had a telescope. I was a child. I had no mentor, and I tried night after night after night, and I just couldn't see it. And it was only years later I found out that a local observatory had kind of public viewing nights to go and look at it, and so I kind of missed my chance. So I'm definitely want to get it this time round.
Well,
there was a comet about maybe 3 or 4 years later that I know my daughter actually did see and responded to. That if she remembers a comet in the telescope when she was really little, it'll probably be that comet that she remembers rather than Halley. But nonetheless, photons from Halley's Comet actually hit her eyeball.
Yeah.
Well, I missed out on Hayataki and I missed out on Hale Bopp.
Oh, those were fantastic comets to watch. Especially Hale Bopp. Although Yakutake was a lot of fun as well.
I did get to see Comet Holmes though. That was one I did get to see, and I did get to image it. So at the time, main space probes that went to Halley's Comet. Giotto. This is in order of closest approach. Giotto. It was also the first close-up color image of the nucleus. Vega 1, which went to Venus first to drop a balloon probe, and then on to Halley. Vega 2 did exactly the same mission profile. Su-Sai, also known as Planet A, they used data from Sakar to improve upon Susi for its dedicated mission to Halley Anna Sak-Arka, which was the first Japanese probe to leave the Earth system, and mainly it was a test of an interplanetary mission technology called ISAS. So basically those were the five main probes, and of course Pioneer 7 did examine Halley's Comet, the Pioneer Venus Orbiter, and the International Cometary Explorer, which was repurposed as a cometary probe back in '82 and visited Jacobini Zinner, which is currently in our skies, back in 1985. And it transits between the Sun and Halley's Comet in March 1986 and took measurements.
Yeah.
So
it's pretty exciting back then.
It was, yes, because I was working for Marconi at the time, and we built some of the instruments on Giotto and shipped them out to S-Tech for integration and testing. So so I got called into the office to watch. They decided week that they were going to activate the boardroom for us, and we were there for the 2 days, and we actually got to see the whole thing live on tele. I was getting all the live feeds from ESA and the Sky at Night special and everything. That was all. We had food and everything laid on. It was wonderful.
Wow.
It's just one of those weird things. And then of course Giotto, even though it was technically damaged, then went on to Grieg Skellerup, and that was another. That I think really that was the thing that allowed us, I suspect, to mount the Rosetta mission in the end, because we proved we could reuse a probe or retask, and not lose out on the science. I think we've been very, very lucky. I suppose for the scientists and the space launch guys, Halley's Comet was probably perfectly placed, because they were able to send this vast armada to it. And I have to sometimes think it's a sad thing we haven't planned an intercept mission to perhaps follow Halley's Comet on its way back in, and just watch the whole process.
Be interesting to see what changes have happened.
Yeah. The real problem with that is Halley's Comet is on a very long elliptical orbit, so you have to have a big rocket basically to get the spacecraft onto that orbit, so it can rendezvous basically and follow the comet around. And
of course the thing is, we've also, since Giotto, we've made quite an impressive improvement in our space probe propulsion as well. We now have ion engines, which are really, really. It's the stuff of science fiction, really, isn't it? I remember reading in Asimov and Heinlein and A.E. Doc Smith stories about electrical propulsion in space and stuff, and I suppose really that's what they used for Flash Gordon in the old penny reels, but
with the little sparks coming out of the Flash Gordon rocket there.
But we've proved the technology with the mission to Ceres,
right, and Vesta as well.
Vesta, and I suspect really we have viable technology. We could accelerate a probe and get it somewhere quick enough.
Yeah. Well, even the Jupiter family short period comets have fairly elliptical orbits, so you're going to have a pretty big rocket engine to change the velocity of the spacecraft to match the orbits of those comets. But I think it's within the realm of possible. We've already gone into orbit around one. So we can do it again. The long period comets, on the other hand, are interesting in different ways, and it would be really cool to be able to study one of those as well, up close and personal for a while. But we'd have to discover it early enough that we could send a spacecraft out to rendezvous with it, and then change its velocity to rendezvous with it, and hang around for a while. And Hale-Bopp was one of the most unique objects in my life anyway, because it was discovered about 2 years before its perihelion passage. So even that 2 years is not enough time to build a spacecraft, launch it, get it out there, and rendezvous with it. So that's going to be a tough project to do someday, until we have those big fancy Star Trek engines, the
Yeah.
warp drive and impulse engine or whatever to get us out there. Something like that might happen sometime, but
I can
it's
just
going to be a little while.
I can see the letter. Dear Mr. Musk, now that you have sent a Tesla car to the asteroid belt, would you be willing to consider this mission? We want to send a probe to Hawley's Comet, or maybe even to 29P Whackman 1.
Oh, yeah, that'd be one to go to. I'd definitely like to see that one.
Oh, I think a lot of people would love to see that one, because it's relatively close. It's a Jupiter family comet. It's relatively close in the solar system. We know its orbit. That's the greatest thing. The orbit is very well known. We know pretty much exactly where it's going to be any given moment of the day.
And it does lots of really interesting things.
Oh, yes. The outbursts alone.
Yeah. Technically, it's not a Jupiter family comet. But it's one of those, outliers that are, interesting in its own way anyway. So.
But say it's something that we know pretty much. We can say how far we can say this far into the future. We know exactly where it's going to be.
Oh yeah. There will be no problem finding it whenever we decide to send something its way.
And I think that was probably the greatest thing about CG was it was another one of these comets that we had a very good orbit for, and we knew pretty much where it was going to be, and we could then set something up and say we're going to send it was the second choice mission at the end of the day, but maybe I think it was the best choice ever. The rest is history, as they say. Poor old little Philae, obviously, but again we learned something.
Yeah, a lot of things.
And like now we have Osiris Rex going out, going to an asteroid, Bennu, as I recollect.
Right.
And we now have a better idea how to land a probe in such a low gravity situation. I remember the little Java game that was up on the ESA website for the Rosetta mission to let you practice landing Philae on the Comet. And I think after about 4 hours, I got to the point I could do it 2 or 3 times in repetition. It would theoretically it had landed and it had stuck.
Of course, reality turns out to be a little bit different.
Absolutely, yes. And I think perhaps that alone in itself has taught us so much more. It's time we did one of those millennial missions and went back to a comet, landed, and maybe even, let's be really audacious, let's take a sample and bring it home. Don't just bring dust from its trail home. Let's actually bring some pristine material home. And of course, with 24p, we would have regular outbursts. Sorry, 29p. And before anybody yells at me, it's 29p. Yeah, I know I got it wrong again. Got it wrong again, Mum. But hey, if everybody was perfect on their comets, it would be a very boring place. No, but okay.
Comets are a challenge because they have so many different pronunciations of names.
Oh yeah.
You mentioned Comet Dutoit earlier. A long time ago, 20 years ago, more than that now, I recovered Comet Dutoit Hartley. And I'd never heard anything about how you would pronounce the name Dutoit. And I thought it was a French name, right? So I was calling it Dutoit Hartley.
Yeah.
Sounds reasonable. And then someone pointed out that Dutoit was from South Africa, so he pronounced his name Dutoit, not Dutoit.
No.
So, okay, you live and learn. I mean, I've heard people call it Schumacher Levy 9, which is totally wrong. It's Shoemaker Levy 9. Yeah. So, they get, it's tough to know how to pronounce all the names of, Churyumov Gerasimenko or Churyumov Gerasimenko, for example.
Yeah. Our favourite one, everybody abbreviates to its number and CG.
That solves the problem. I used to joke, I think, with David Levy, actually, among others, about Comet pronunciations. For example, Swissman Walkman 1 became Sony Walkman 1 because back then Sony Walkmans were popular.
Yeah, I can well imagine it. And of course, the other one everybody has issues. It's spelt wild, but it's pronounced Wild.
Wild, yeah, Wild 2.
Yeah.
Or
And
Wild 1.
for a while, I was calling it Wild 2, and then someone says, "Hang on, it's Wild." I thought, "Oh, yeah, okay, it's Wild."
Right. Yep. So it'd be nice to have sort of a library of Comet name pronunciation, so everybody knows how to pronounce the name as the discoverer would have pronounced his name.
Yeah, write them out phonetically so we all know what we're doing.
Well, I think the most famous one is of course Halley or Hawley, not Haley. I still get
Haley, Halley, Holly. Yeah. Which is it? I think he pronounced it Holly, right?
The word, from what I understand, it was pronounced Hawley.
Yeah, I've always pronounced it Halley.
Halley is fine. It was okay. Hawley was either most people either use Halley or Hawley. Some people still say Haley, as in the rock and roll singer. And I have to remind myself of the video of Sir Patrick Moore, as he was then. Someone actually called it Halley's Comet. And he goes, no, it is Halley's Comet. Quite correctly, it would be Hawley's Comet,
right?
Not Haley, who was actually a rock and roll singer who had a band called the Comets. So, yeah, the most infamous one is obviously that one. But as I say, a lot of these names, we're not used to them. I still stumble with Warichet's name on occasion. I have issues with some of the Japanese names. It's just because we're not used. It's something we're not used to. But as I say, in the end, it works out because we hear other people using them, the names.
Yep.
And so that's how it's supposed to be. Okay. If I'm getting really lazy, I'll say it's 29p SW1.
Yeah, and even SW1 isn't really, or Swissman Walkman 1 isn't really correct anymore because we've sort of gotten rid of the numbers of the periodic comets. So Wild 1, Wild 2, well, no, that's not anymore. They're both Wild, but you have the number that distinguishes them apart. So I still use all the numbers anyway. Swissman Walkman 3, is a different comet from Swissman Walkman 1,
Well, yeah, because the way I've always understood it, there's 73p and there's 29p.
Mm-hmm.
So 29 was the one was SW1, and 73 was the second one they discovered. That's the way I've always had it explained to me. Okay, obviously.
Well, the numbers come now from when the object gets observed a second time, and you number it. So it's not necessarily the second of that person's comet discoveries that returned. It's the second one to get recovered. So I don't even remember which one is Scotty 1, Scotty 2, Scotty 3. They're out there somewhere, and I don't remember whether Scotty 1 is the one that's numbered or anyway.
Actually, I just checked something. 31p is SW2, 73p is SW3.
Right.
That was his third comet.
Yeah.
So
in those cases, they're sort of that way just because comets were not discovered as often back then, I think, and it took longer between comet discoveries. That they get Also back then, the numbering scheme wasn't in place, so 1P Halley was called that because it was the first periodic comet to be recognized. 2P Yankee is the second one, and so on. But then once we had numbered the ones we already knew, then we start numbering the new ones, and they get out of order now. So we're not supposed to call them by numbers. So
I think the reason a lot of people still used SW1, 2, and 3 is because it automatically which one. You don't, if you've not got the 29p. If I say to you, I was looking at SW2, you're going to know I mean 31p, the 31st periodic comet to be discovered.
Right.
So.
Yeah. And I still call, all those numbered comets by their numbers, like, Temple 1, Temple 2, and Vild 1, Vild 2, and all those, we think of them in terms of, we know who the comet is because that's what we used to call them when we observed them.
Yeah, and that also is a way of saying, okay, I'm talking about their second or third or fourth comet, not the first one.
Yeah.
Because if like Vild has 2 comets, if I say Vild 2, automatically everybody will know which comet is being talked about. I could just simply put a caption up, this is Vild 2. Not very scientific, but it automatically identifies it. Whereas Johnson has 48p, and then now it's there's also a Johnson 2015 V2. So by saying I'm talking about 48p tells us.
It's also a different Johnson.
Yeah. Which really does confuse people. A lot of people think, oh, no, different discoverer completely.
Yep.
It confuses me, that's for sure.
But, well, that's our job, is to confuse people. Yeah.
Absolutely.
It keeps our grants coming in, doesn't it, Jim?
Yeah. If everyone else knew what we knew, then there wouldn't be a need for us to get paid to do this kind of stuff. So,
but ironically, the fact is, most people, it's that there's an attitude of lazy science out there. Oh, I can't be bothered. I'll let somebody else do the hard work. Having said
get
that,
the name on the discoveries, then
that's the best thing about it. Okay, if you want to be that lazy, be my guest. But guess what? You being lazy, hey, I just got a comet out of it, or an asteroid, or whatever.
That's a whole other subject.
Oh, absolutely. And of course, saying that, of course, June 30th is Asteroid Day. So that's a fun. That does actually fall within, I suppose, the show's remit. I'm going to go for it. I know what the June Mary, we know what the June show is now.
Yep.
But it's nice in a way, and I think a lot of us should start paying attention to SOHO. Just looking at the number of discoveries being made by our old friend Tegrev, by Wachot, Rainier. There's tons of comets we just don't get to see, but get caught on SOHO's images, and then it's just a battle of making sure that you're the first person to see the image and stick a report in. You may end up sharing it. I don't care, but it's still part of the fun. I suppose really. It is a neglected part of our hobby. Most of us are just clued into night sky observations, either running your own equipment in survey mode, and then just looking at the take the next day.
Well, that's one thing about modern comet discovery, is that the surveys now cover enough sky that most of the comets will get discovered when they're fairly far out from the sun, long before they get bright enough for the amateurs to find anymore. So unfortunately, I think we're on the verge of retiring amateur comet discoveries, although they sneak a few in here and there.
Well, there's still places that the big surveys don't go.
Yeah. Well, even them, if you can cover the whole sky, literally 360 degrees of sky, over the course of, you have to wait for the sun to move out of the way, but if you do that from year to year to year to year, you're going to find even the comets that are going to be buried in the sun and hard to discover with an opposition survey, but they would have been found 2 years earlier when they were at opposition or somewhere away from the sun where you could discover them. So very few comets would come in. In fact, it would be a really unusual comet that would come in from behind the sun, go around the sun, and go back out close to the sun, while the Earth is in the right place for that to happen. Anyway, the big surveys that cover most of the sky are going to take that little hobby away, unfortunately.
Well, we'll see. I still think there's a lot us amateurs can do.
Yeah, there's certainly plenty of room for amateurs to observe comets and understand them better and things like that. So.
And certainly get the images, because really the professional scopes don't have the time. if it's a famous comet, they might do some publicity stuff and image the comet and put it up as for publicity purposes, which is all good and fine. I realise that they're like everybody else. They need funding, institutional funding. Is the only way they're going to get it, and that's people putting in requests.
There are very few professional comet observing programs that can look at a lot of comets. They might look at a very small subset of them and try to understand what's going on in those comets. But imagine being able to observe every comet that went by in a way that would allow you to really keep tabs on the thing and really figure out what it's doing. How often do comets split, for example? We have an idea because we've seen a lot of them happen, but we only see the big spectacular ones, the really subtle ones, or you could have a little piece fly off of a comet, and by the time someone will be able to observe it from the ground, it'd be gone, and they'd be able to tell that even happened. So learning about a lot about that kind of stuff would be a fun program to get going.
and of course we have the instruments and we have the time. Even right now I'm in the middle of I've got my scope design set up. It's a half meter. It's f3.3, which is unheard of for a long time for an amateur scope. The first scope I bought, which was a Newtonian, was f4.5. My current Newtonian's f4.5. Now f3.3 mirrors are available in the larger mirror sizes, which was something that was never happened before.
The Celestron telescopes, and they're f8 or f10 or something like that, so they're very long, very slow instruments for that kind of thing.
But the camera technology is improving all the time as well, isn't it?
Sure is.
Well, it's the trickle down is even quicker on CCD technology. Is even quicker than at first. Originally, these were cameras that were built for the military to use on satellites and stuff. Then then they got declassified, then into the hands of a few well-off amateurs, financially speaking, and then the manufacturers cottoned on that there is a whole bunch of people out there who would pay sensible prices for this technology. So then once the business model was there and there was the need, and let's face it, beforehand everybody was using 35mm film. You were having to hyperize your films. I remember reading about David and Eugene and Gene doing their hyperization sessions prior to an observing run, and like having to be really, really careful so not to ruin the films with accidental exposures. And if anything, the fact that they had ruined film is what gave us Shoemaker Levy 9. Thank you.
David pronounces his name David Levy, so that's part of the story of the discovery of Shoemaker Levy 9 is they had really poor weather the night they took the images, the discovery images, and because they had some film that they thought might be light struck, they were able to not worry about wasting film on a poor night of observing. So they took the images when they did, and they might have discovered the object, the next week or something. But who really knows? And that's the beginning of a fairly fun
period of time,
year and a half or so of observing Comet Shoemaker Levy 9.
I think the fact that it was discovered that early really allowed the astronomical community to gear up and get the observing sessions set up and to get the information. The fact that the Hubble was had just been refurbished as well and was going to be they didn't really want to use the scope. They wanted complete testing. I can understand that they didn't really want another faux pas they had when they first commissioned it. But they rushed the Hubble into service for this event, and I think that was probably the greatest thing. The Hubble was available. There was nothing booked at that time. they could put it into play. They could get it looking at the right place, and it really, in a lot of respects, revolutionized our thoughts on comets. I know that Spacewatch was the biggest benefactor from it, because being able to show night by night the impacts made people sit up and realize what could happen to this, to Sagan's pale blue dot.
Yeah, that was the first. We don't really even know for sure whether the progenitor that became Shoemaker-Levy 9 was an asteroid or a comet, because it could easily have been just an asteroid that got shattered into pieces to made to look like a comet. We don't really know for sure what it was really, whether it was more cometary or more asteroidal before all the events started. But yeah, finding that object, as you probably have heard the story, I was involved in confirming that comet discovery, and that first moment of seeing, I was the first person in the universe to see Shoemaker-Levy 9 in all its glory, with all the different pieces. The discovery images were with a smaller telescope, and all they could see is the long trail, and then the wings of dust, which looked like tails, coming off of it. And when I saw it go by, I'd been observing comets for quite a few years at that point, and I thought I'd seen everything comets did. Well, I learned from that comet in particular that comets do even more interesting things, especially when you think you know everything about comets. They'll come and do something new that you've never seen before, and that was certainly a case of that. And to be able to see that, first of all, I saw the one tail, which turned out to be a dust trail rather than a tail, and then I saw the second tail, and I thought, wow, that's pretty cool. It's got two tails. And then I saw, not only that, it's got a bunch of nuclei, not just one. And then it's got a second tail, or a third tail going off the other direction. And it was, whoa, this is really, wow. And it was a little after that I talked to David on the phone and told them that their comet was real. And wow, was it real? And I remember talking with Gene Shoemaker that night on the phone right after that. And because it was so close to Jupiter, we even talked a little bit about whether it might have just flown past Jupiter and broken up because it passed near Jupiter.
Yeah.
We didn't have a clue that it was still in orbit around Jupiter and would go barreling into the planet the following summer. So that took a couple of months of observing to nail the orbit down and confirm that was going to happen. So that was just a really exciting time in my career, that's for sure.
And it's one of those, I think, that probably made Mr. Marsden's day for quite a few days, trying to asking people for more information. So the orbit, because he was actually one of the old-fashioned computers. He did everything by hand, didn't he?
Well, he still had computer programs that would do a lot of the work, but it was much more hands-on probably back then. But it took from March until I think it was May when the first Jove-centric orbit was computed, and the possibility that the impact would happen the following year was first recognized. So it took a little bit of time, but I've certainly probably contributed maybe half of all the observations of the object during that time period before we knew that it was going to hit.
And of course, since then we've had we still don't know whether Anthony Weasley's object was a comet or is it just an asteroid, but we've seen it happening more. Chris Goh had one as well. So since Shoemaker-Levy 9, we've had at least two more well-documented cases of impactors on Jupiter, and it was certainly, for me, I remember reading the bits about the craters marching in a straight line on the moons, and maybe this is just a massive whack around the head we're now getting with a cosmic 2x4. Hey guys, this is what's possibly caused it in the past.
Yeah. Well, one of the things we recognized shortly after Shoemaker-Levy 9 was discovered, with the long train of nuclei all in a straight line, back during the first Voyager flyby of Jupiter, they took pictures of all the Galilean satellites and a few others, But what they discovered on Callisto were a bunch of crater chains.
Yeah.
And we'd seen crater chains on our own moon, but those pointed back to a primary impact crater. And these crater chains on Callisto did not point back to a primary impact crater. So there was a puzzle. What caused these? Where'd they come from? Is there something we don't understand that went on here? And as soon as Shoemaker-Levy 9 was discovered, we had an answer.
Yeah.
That's how you get crater chains on Callisto, and there's a number of them that were documented, and it was an interesting sort of side effect of Shoemaker-Levy 9 as well.
Yeah, and I must admit, the fascinating thing for me is the fact that we can now apply it and maybe think, yes, we have a smoking gun for the dinosaur extinction, Chicxulub.
Yeah.
Now, has there been other impacts that have caused minor extinctions, which the craters are now either been filled in or been erased through plate tectonics? Was there previous indications that it's happened to us? We just can't find it anymore. So it really makes you think that, yeah, Jupiter is kind of nice to us at times. It sucks in all the debris and occasionally disrupts the comets, gives us a nice lights display in the sky. But it has the other side where it can actually deflect stuff into the inner solar system.
Yeah.
And maybe even paint the bullseye on us.
Well, it's really because of Jupiter that there are as relatively few asteroids out there as there are. If Jupiter hadn't been there, the inner solar system would have been just covered with asteroids, and impact rates on Earth would be 100 times or something what they currently are. So in a sense, Jupiter is the good guy and the bad guy, because it cleared out the solar system early on and decreased the impact rate for us today, but it right now feeds us impactors at a rate that is significant. So it's a lot lower rate than it would have been, but it's still a rate that we ought to at least be aware of and concerned with. And how often does a big enough impactor happen? I just read an article that suggested that mass extinctions are actually almost all related to Earth-related processes, like the equivalent of global warming or climate change due to volcanoes and things like that. And very few of them can be identified as impact-related, which I thought was, I figured maybe half of them would be impact related, but apparently it's a smaller number than that, even, surprisingly. So most of the big impacts actually happen in places that don't cause as much global mass extinction, whereas the Chicxulub impact happened in an area that generated basically acid rain and a much more serious atmospheric condition than an asteroid of that size apparently normally would. So I think there's still a lot of arm waving going around on that, but it's an interesting thing to consider that, as bad as impacts are, and we better find out, whether an object's going to hit us so we can do something about it. It might not be quite as super critical as we used to think it was.
True.
But it would certainly kill a lot of people if an asteroid of a given, even the 1 kilometer, 2 kilometer sized asteroids hit us. They would definitely have a global effect on humans, but it won't
one
cause
thing
mass
that
extinction.
the discovery of a Maua's proven is that we're having stuff coming in from outside as well. So, did I read is there another satellite being launched that's going to be picking up these things quicker? I'm sure I read something when there was. I heard something about it at Astrofest, because there was a lady there that gave a talk about Maua, and it's probably now thought that it's quite common for asteroids from elsewhere to come through the solar system.
I've been waiting for more than 20 years. I read a paper when I was a lot younger about what you would learn by seeing the first truly hyperbolic object fly through the solar system. What we did, we have a lot of arm waving going on with star formation and the formation of planetary systems, what fraction of the material in a early solar system as it forms gets ejected? There are some constraints that say it's about the equivalent of roughly the mass of what we see today, or it could be 10 times the mass of what we see today. We had no idea exactly how often that would be, but all this stuff gets ejected a lot of it gets ejected completely out of the solar system. So there's a lot of interplanetary debris that's out there that would come from the formation of planetary systems. And when we start finding ones passing through our system, we will start to be able to say something about how much debris there is out there between the stars, and how much debris gets kicked out when planetary systems form. So I've been waiting for that to happen, and well, we finally did see one. It took longer than I expected, actually, based on the paper I'd read all those years ago.
Well, looking on Google, I see 2 hits for spacecraft for asteroid detection. One is the Sentinel Space Telescope for the B16612 Foundation, and B16612 studying small sat missions to search for near-Earth objects. So those are one of them. Actually, the second one is a spacenews.com story.
Sounds like the same telescope tube in both cases, though.
Yeah.
It was B6112 in both cases, or 612.
They say that they've shelved the Sentinel project to in favour of the concept of using smaller spacecraft. So,
Well, we've found all the big ones, right?
Yeah.
There might be some, say 5 to 10 kilometer object that's in an unusual orbit that we can't see very often that might still be lurking out there. But the last time I heard, we discovered something like 95% of the kilometer and larger near-Earth asteroids, and those are the ones that are dangerous on a global level. Objects that are smaller are bad if they hit you directly. But they're not likely to kill a lot of people on a global scale, like the objects bigger than about a kilometer start to do fairly effectively. So the dinosaur killers, I think, are solved, except for one problem, and that's a type of object we've been talking about, especially earlier in the show, namely Oort cloud comets.
Yeah.
A comet coming in from the distant parts of the solar system, we have at most a year or two of warning time, and if it's on an impact trajectory, you don't have any time to do anything significant with the object other than, well, leave Earth, I suppose.
Yeah. Well, that was what killed the dinosaurs. They didn't have a space program.
They didn't. Yeah. Yep.
I know everybody thinks it's a joke, but in reality, if you think about it, it is very, very true. If you're planet bound and you have no way to say move start a colony, say on Mars or something, to be a fallback position for an impact, for a major impactor, then you're not. I don't. Well, it depends. I know a lot of people say, "Oh, we'll build shelters underground. We'll go underground for X number of years," but you've still got
no food to grow.
Yeah.
Exactly. You've got to find a way to grow food, and you've got
you're not going to be able to do that for the whole population on planet Earth.
Exactly.
And I'm not just limiting ourselves to humans, but all the other creatures and flora and fauna that inhabit the planet. That's going to be a very bad day if that were to happen. But we can deflect asteroids, and we can, populate other worlds to spread ourselves out. I think to allow humans to exist longer. So it's a tough problem, but I think we've solved the biggest part of it, and it's time to, we go to smaller sizes. We find fewer of the smaller objects. The smaller objects, if they hit you, that would be a bad day. Like Chelyabinsk is a good recent example where an object that was something like 18 meters across, it smashed into the Earth. Well, actually, it ran into the Earth's atmosphere and shattered into pieces before it got to the surface. 50,000 years ago, an object that was maybe 4 times that size and a nickel iron asteroid smashed into Arizona and cause meteor crater. So those kinds of things happen, but they would only damage a very small area of the planet. Something like 1,000 people were injured by the Chelyabinsk impact. And it was mostly because they got hit by flying glass and debris from the sonic booms, the explosion in the upper atmosphere that propagated a sound wave basically that shattered glass fairly effectively on the ground. So there's a couple of things I learned from Chelyabinsk. The first thing is, boy, Russian people have lots of dash cams.
Yeah, well, I think their biggest issue is
their insurance, isn't it?
Yeah. The second thing I learned is enjoy the fireball, watch it, enjoy it, and then get away from the windows.
Right. The videos showing those sonic booms, though, the sound of them, you would have been, if you didn't know what was going on, didn't understand astronomy, you would have been terrified.
Yeah, you wouldn't have any idea that was about to happen. But you do have something like a minute, for those sound waves that are tens of kilometers away from you to propagate down to where you're at. So, enjoy the dash cam videos and get away from the windows.
And of course, we still don't know what caused the Tunguska. Tunguska, thank you.
So we have a good idea, and we know there was an object that was on the order of 100 meters, 50 meters to 100 meters across, about the same size as the meteor crater object, actually, except it exploded above the ground rather than making it all the way to the ground like the meteor crater impactor did. And we know roughly how much impact energy it exploded with, something like 10 to 20 megatons, and it would have looked a lot like a nuclear bomb, except it was before the age of nuclear weapons. So happily, nobody saw it happen and said, "Oh, someone bombed us. We're going to retaliate." So we had 50 years almost before nuclear weapons appeared, and we were able to recognize that was an asteroid rather than the enemy bombing you. So an object like that would have to hit a city in order to kill a lot of people. And it killed probably some deer and other creatures, of course, and knocked down a lot of trees where hit. But most of the planet is water, first of all, and second, empty. The number of human heads that you have within the explosion range, if you randomly picked a place on the planet, usually nobody and nothing would be killed, or no humans anyway. So
maybe you'd see a light in the sky if it was a nighttime explosion, and you might feel the effects of the sonic boom. But
you'd see a flash in the sky in the daytime too. That would be pretty bright. What we really need to do is get Rich Kowalski on the show because he's the only human being to ever discover an asteroid that later hit the Earth
and get a piece of it.
And he did it twice.
Yeah.
And all the rest of us have discovered asteroids, but none of them have hit the Earth yet. So it would have been good to have him. I'm sure he'd be making comments here, and his head would be about twice as big as normal right about now.
Well,
I think I spoke to him about that last time he was on the show, actually.
Yeah, I think we probably did bring that up.
The last time we had.
He better start observing.
Yeah, the last time we had you, Rick, and Rich on the show, it was quite good fun. It was our longest show ever.
and amazingly, you invited me back on.
Well, yeah. As I say, the great thing about having you guys on is the fact we can throw in. We can bring up the subjects, and it stops being. I like the format of saying, of bringing up a subject, and it's letting it flow from that, and that's the greatest thing with you guys. Put the subject out there, and it's great because we get it's different points of view, and it's not like a question and answer session where it's very stilted. That's one of the things I've noticed. If you're doing questions and answers, instead of just letting your guests discuss it, you get much. I think it's more educational.
Mm-hmm. And it's a lot of fun for us to talk as well, because you get us talking about subjects that we really have a lot of fun with. And
Yeah. And I've just looked. We're actually coming up to 1.5 hours. We're at 1 hour 24, so I think we've done quite well. I'm going to get yelled at, but I don't care. Because if push comes to shove, I can. It will take me about half a day, I suppose, to learn how to do podcasting, and I'll still get the podcast out without any cuts. But that's the other great thing about Astronomy.FM. Shows like this, normally they all the main shows stick to an hour as the tops, but for something like this, they just love to let us go on and talk about whatever our heart's desires, including fantastic missions to comets and stuff like that. We would love to have done if the funding was there. Well, I'm going to make the producer's life a nightmare. We've been here for an hour and 25 minutes. Jim, it's been brilliant having you back. I really wish Neil was here, because I know how much he likes talking with you guys as well, and he always seems to miss these ones. I feel sorry for you, Neil, because every time we had you, I think he was here for one of the shows, then we had you guys back, and he wasn't able to attend.
Yeah.
But I'm gonna get all three of you back at some point. I'm gonna definitely do that, and
yeah, that would be good.
It's always good fun with you guys.
The biggest obstacle is the time difference, because right now it's 2:30 in the afternoon here.
Yeah,
and it's getting late over there.
And
although being astronomers, you guys probably stay up late anyway, like I do, you know.
Well, it's 5:40 for me in the afternoon. I'm still in upstate New York at the moment.
Yeah, it's 10:40 for me.
So that's pretty early for you then.
Yeah, it is actually.
Except you're not outside with your camera taking pretty pictures for us.
I will be later.
I look forward to seeing them.
Well, one quick question for you: how would an amateur astronomer we'll say they've got at least an 8-inch, maybe a 10-inch scope, definitely got a CCD. How could they get involved in things like Spacewatch and stuff?
Well, I don't think, short of applying to be a team member and observe with us, we only have a small group, and I know the Catalina Sky Survey has a group as well. I mean, there's maybe an opportunity to apply for jobs with us if they have the skills, the background, maybe in programming or observing. But I think there's certainly a lot of opportunity to do things like photograph comets and stuff with their own small telescope in their backyard.
And of course, you can always track near Earth objects with your own home telescope.
Yeah, you can see. Yeah, you can see some of them, or you can see Elon Musk's Tesla, maybe, if you know where to look for it.
Yes, it's still being picked up, I believe.
Days after lunch.
Yeah,
we did observe it for a couple of days afterwards. So, so there are lots of opportunities, I think, to contribute in other ways. Especially, when a bright comet gets discovered, we're really way overdue for a nice big bright comet. Something like Hale-Bopp.
We really are. We so desperately need one.
I was talking with my wife's astronomy students and talking about Hale-Bopp, and there's been no real comet since they've been alive that was anything like that. So we're way overdue for a nice big bright comet like that. And we had some close approachers like ISON, but that wasn't really the same kind of thing. Hale-Bopp, where you go out for a month every morning and look up in the night sky and see the spectacular comet. That was a lot of fun. I enjoyed that. So.
I didn't have a telescope at that time, but I enjoyed watching it every night. It was gorgeous.
Yeah, that's for sure.
Okay.
I got lots of pictures of it, so yeah.
we're coming up on the half hour, so as much as I would like to keep this going for the next 3 hours, I'm going to let you. I know everybody's got stuff they need to do, so Jim, thank you for coming back and having a chat with us. It's always great. We're going to get. I think we really do have to get together with you and Rich and Rick at another time and just have a good evening's natter. Mary, thanks for joining us. It's always great having you here. Neil,
thank you very much.
I'm going to send you the uncut version. just so that you can sit and listen to us. So I know you'd be happy there. So I'm going to say good night.
And
Well,
good
thanks
night.
for having me, guys.
Thanks for coming back, Jim. It was awesome.
So good night, everybody. Clear skies, and see you all again soon.
Bye.
Bye.
Bye-bye.